All right, here we go. So today's class will probably be a little quicker than usual. Maybe we'll end at the 2.5-hour mark because I don't have much to talk about after support vector machines. But anyway, so we're going to cover one cool topic. It's another machine learning classification algorithm that's, there's a whole plethora of different ones out there. But this one was very popular back in the early 90s. Before neural networks came back and resurfaced, it was very popular. So that's taken preference. So there's, there's a little bit of push and pull. It's an algorithm called support vector machines, and I'll talk about what exactly those are, during this talk. We'll talk about the cost function you have to minimize, concept of large margins and kernels, and then just a quick SVM demo that we'll cover in MATLAB. So our goal for this class is to not actually optimize the cost function for SVMs, because it's actually quite difficult and it's beyond the scope of this course. So it's accepted practice to actually use dedicated libraries that actually solve support vector machine problems, like libsvm or any of the MATLAB toolboxes. So we'll be taking a look at just how to use them, and I'll cover enough theory for you to, to understand what's going on. But in terms of implementing them, we're not going to do that for this course. We're going to actually just use them instead. Okay. And then there's something else I didn't talk about, which will be quite nice. It's about how you actually go about in designing a machine learning system. So I've only talked about the different algorithms and a way to actually find the right parameters and all that, but I haven't really talked about how to start from the beginning to the end. Well, which algorithm do you choose? What's the best algorithm do you choose? What's the right number of features you choose, or all the different intricacies and the different architectures that you can figure out in order to design the right algorithm to do so. So stuff like cross-validation sets and bias invariance and learning curves, and I'll talk about that later in this talk. Okay, so just a quick couple of notes before I start. The first one was I sent a little note last week. There's a little bit of a fundamental flaw in the algorithm that I discussed towards the end. If you wanted to implement that in MATLAB code, there was a little bit of a problem with the regularization step. I've corrected those notes last week, but I just wanted to make clear of what the changes were this week. So this was let me see here, where was it? So this was the step that I covered the last week. There was a portion here where when I was accumulating the gradient and the costs, I was introducing regularization. Here you actually don't do that. What you do is you wait for all of the gradients to accumulate, so you cycle through all of the different training examples, and then when you're finally done, that's when you put in the regularization. So this stuff here is just accumulating normally without any regularization, but then at the very end, which is the last step, you introduce it at the very end. So once you accumulate everything, once you finish that up, then you add in the regularization term. So you just basically add lambda over m, and then whatever the weights were before you started updating, you add those into every single weight except for the bias term. So that's there. And then you finally add regularization to the cost. So once you accumulate the cost for every single example, once you're done, then you add in all the regularization. So you're just adding up all the weights squared without the bias terms itself. So these notes were corrected the last week, which you're able to download. I just wanted to reiterate that point. And then last but not least, final exam information has been released. I don't know exactly the details behind how the format is. I don't know how many questions. I don't know how long it's going to be. I'll figure that information will come very soon. You will know very well in advance how it's going to be structured, before the final exam. But the date will be April 26th, which is on a Tuesday, and the time will be between 3 and 6 p.m. So it'll be a 3-hour exam. And depending on what section you're in, there are different rooms you're writing. So we're actually going to occupy most of the Xi building. So that's pretty cool, I suppose. So for sections 1 and 2 for the undergraduate stream for ELE 888, that's you're in Xi building 554. And sections 3 and 4, you're in Xi 652. And the graduate stream E8209, you're in Xi 540. So this information is already posted on the website. I just wanted to officially make that clear to you, because it is actually my duty to actually physically tell you that yes, final exam information's here, this is what it looks like. So that's actually supposed to tell you that. So more details will follow regarding the format and what you're going to expect on it and types of questions. That'll come later, because I haven't actually thought about it. I actually have about a month to design it, so haven't really thought that far. Okay, so let's get on to support vector machines. They're the acronym, or there's a very popular acronym. People just call them SVMs for short. Just when you see support vector machines or SVM, they mean the same thing. Okay, so it's yet another machine learning algorithm. I guess yet another. There's several that we learn. You learn logistic regression, and recently we learned neural networks, and now we've got support vector machines. So there's a whole bunch of different algorithms that we've covered, and each of them have advantages and disadvantages, and we'll cover those as we go. So it's another machine learning algorithm. So this was the preferred algorithm back in the early 90s, before, neural networks were actually used quite heavily in the early to late 80s, but the reason why they fell out of favor is because they actually took a very long time to train. So with the current available hardware and the current algorithms that you use to optimize, like you pretty much use gradient descent, it takes a very long time to train these things. So that's why they kind of fell out of favor for a while, until the latest craze that Google introduced. And also, you've got good hardware and lots of data, and that actually made it popular again. So these were the preferred algorithms over neural networks. I'm going to acronym this as NNs, or neural networks, just to save time, okay, in the early 90s. So this was the craze back in the early 90s in terms of classification and all that. Okay, because neural networks were hard to train. It's mostly because, computationally intensive. With the available hardware. Okay, all right. Okay, so the reason why support vector machines are very powerful is because there's a guy from Microsoft Research who actually designed a very highly advanced, optimized algorithm in order to train support vector machines, which took a fraction of the time over training a neural network. So that's why they were actually preferred in the early 90s. So it's a technique called sequential minimal optimization. That's just a little bonus. We're not actually going to cover that. It's actually beyond the scope of this course. It requires knowing advanced optimization algorithms, which we're not focusing here. We want to focus on actually being able to use these things. So SVMs were easier to train due to a highly advanced optimization technique known as sequential minimal optimization. So it's called sequential minimal optimization, which is an acronym SMO. Actually, if you use the the SVM toolbox in MATLAB, the default optimizer is sequential minimal optimization. You'll see that it's SMO. Yeah, I know. It just restarted. Oh, shoot. You know why? This freaking cable is very sensitive. Just let me plug it in. Sorry. Sorry, I knocked it and then. Yeah, sorry about that. This thing is very sensitive. For a minute, I thought the computer restarted. I'm like, oh, crap. Anyway. Okay, so sequential minimal optimization. Okay, so here's a quick note. We will not implement SVMs in this course. It's actually quite advanced. We're just going to use the available toolboxes that are around in order to help us, do this stuff. But we need to know a little bit of the theory in order to figure out how to use these things. Right? We will not implement SVMs in this course. Right? We will. Oopsie. Instead, use available tools, like MATLAB or whatever. There's also a very popular library called libsvm. It's very popular, so that can be used as well. But just wanted to tell you that there's different tools out there to do the same thing. Okay, so the basis behind support vector machines is that they're known as what's called large margin classifiers. And what large margin classifiers means is that it tries to find the decision boundary that will separate between the two classes the greatest amount possible, large margin. Okay, so SVMs are known as large margin classifiers, and I'll show you what I mean in a minute. But they're called large margin classifiers. Okay, large margin classifiers. So what I mean by large margin means to find. Actually, let me just double check to see if I'm still recording. Okay, good. Just want to make sure that that little hiccup didn't kill the feed. Okay, large margin means to find the decision boundary that minimizes, or sorry, not minimizes, maximizes the distance between training examples in different classes. In different classes. So I'll show you a couple of diagrams just to make clear what I mean. Okay, so before I do that, all right, I need to cover a definition. And in a lot of SVM text, literature and a lot of textbooks, people talk about a hyperplane. I touched briefly on that maybe at the beginning of the course, but I didn't really make clear what it was. So I need to define what a hyperplane is first. So let's, suppose we got some training data, and we want to plot them on like a 2D plot or a 3D plot. We just want to plot them so we can visually see what they look like. We have some training data, and we want to plot them on a graph. Okay, so we're going to assume two classes for now. We'll talk about the multi-class case later, but just for now, we're going to assume two classes, just to make things simple. So we're going to assume two classes. Okay, so when you're dealing with two features, as we've seen, the decision boundary is usually a line that separates between the two classes. That's just for two features, right? When you go to 3D, when you go to three features, it's going to be a plane, a two-dimensional plane that'll separate between the classes, right? So let's see here. So for two features, the decision boundary is a line. So something like this, like you've got a graph like this, and you have two different features, and you've got a bunch of points, and then the decision boundary that separates them is a line. That's nice, right? So this is your decision boundary. Okay, that's fine. And then when you go to three features, it's almost the same. So instead of having a line, it's going to be a plane or a kind of sheet that separates between the two features. Or sorry, not two features, two classes, right? The decision boundary is a plane, right? So something like this. So we've got three features, 1, 2, 3, and we've got a bunch of points over here, and let's say a bunch of points over here, and the best separation is like a plane. So something like that, I guess. There's a plane of separation that separates between them. Okay, so this is your decision boundary, so to speak. Okay, but then what happens when you get to, let's say, larger than three features? Let's say 5 or 6 or maybe even 100. So there's no way you can actually visualize this. We can't go beyond 3. So what people usually describe the decision boundary when you go to n dimensions, it's what's known as a hyperplane. It's a hyperplane of separation between two features, right? So you've got plane here in 3D. Hyper means that you're going beyond 3 dimensions because we can't really visualize it, but we know that there's some thing of separation that'll be able to separate between two classes when you go beyond 3 features. It's what's known as a hyperplane, all right? So let's see here. So anything beyond 3 features we can't visualize. Okay, so what we do is we call this decision boundary a hyperplane. Hyper in the sense that we can't really visualize it, but we know that something is there to be able to separate between the two classes. It's called a hyperplane, so that's the formal definition. Okay. So when you have n features, the goal is to find an n-dimensional hyperplane, right? So if you have 2 features, then it's a 2-dimensional hyperplane. If you've got 2 features, and so on. Okay, so for n features, actually it would be n-1 because there's n-1 independent variables. So for n features, the goal is to find a n-1 dimensional hyperplane. The reason we say n-1 is because one of the variables is not, it's dependent on the others, right? So if you wanted to plot a line, x1 is the independent feature and x2 is the dependent. So there's only one variable that you're varying, right? So it's an n-1 dimensional hyperplane. Okay, so I just wanted to lay out what a hyperplane was. Okay, so basically the goals for support vector machines is that it finds the optimal hyperplane that separates between the two classes. So what I mean by optimal, I'm going to talk about in a little bit. So SVMs find the, what's known as the optimal hyperplane. The optimal hyperplane, okay? Separating between two classes. Two classes. Okay, so what does this mean actually? What exactly does this mean? So what does this mean? Okay, so let's consider the two feature case just for now. And let's just assume that the features are linearly separable, just for now. Okay, for now. And features are linearly separable. So what I mean by linearly separable is that there's a clear decision boundary between them, just for now. Okay? But in general, this concept can apply to as many features as you want. So in general, this concept, it applies to n features, as many features as you want. It doesn't have to be 2. But we're just going to consider 2 because we can actually visualize this. Okay? Okay. So let's say I have this diagram. So let's see here. Not screenshots, but oh, where am I? Oh, sorry. It's the Google Drive. There we go. Can't remember where exactly. It's this, not this one. That one. Okay, good. Okay. So let's say, here's a pictorial example. So let's say I've got two classes, right, that are separated in space, and then each one of these points is delineated by the class they belong to. So red belongs to one class, the circle belongs to another. Now, there are many different lines of separation that will separate between these two classes, right? You have this line that'll separate them, that's fine. You have all these different lines, but which one do you choose? Which one is the best line of separation to choose that'll separate between these two classes? SVMs figure out what the best line of separation that is, okay? So there are many possible lines of separation, or decision boundaries is, lines of separation, to separate between the two classes. Okay, that's fine, that's cool. Okay, which one is the best one? Because there's so many different ones, right? Which one's the best one? Okay. So intuitively, what you probably think is you want to choose the line where on each side of the line, it's the farthest away from any of the examples as far as possible. So you draw a line of separation where on one side, it's as far away from one side of the examples, and on the other side, it's far away from all those examples too. So this is what we mean by large margin. It's the line of separation where it maximizes the distance between the line and each of the classes. So that's the optimal one that you want to choose. Okay, so choose the line that is the furthest away from the examples. So that's the philosophy we're going to endorse. So this is what is known as a large margin classifier, or a large margin hyperplane. So this is what is known as a large margin. Also, people like to call it a large margin or maximum margin hyperplane. Oopsie. So large margin or maximum margin hyperplane. That's what people like to usually, So basically, what the philosophy here is that you want to find a hyperplane that has the largest minimum distance between an example. We're going to call this D. So find the largest minimum distance to the training examples. Just examples by itself, okay? And we're going to call this distance D. Okay? So here's another diagram just to be sure that we know what we're talking about. So this is just taking the same points, all right, and figuring out what the what the optimal hyperplane or the optimal decision boundary would be. Okay, so we're going to call the distance between the line and then any of any of the points where the minimum distance from the line to any of the points is d. So the distance here would be d. Okay, and also the distance here would be d. So on each side of the hyperplane or on each side of the line, the distance is equal. So the margin is defined as twice the distance. So the margin, the distance between one set of examples and the other set of examples with respect to this hyperplane, the definition is twice that much. Okay, so the margin is defined as 2d. It's twice the distance. Okay, that's great. All right, so let's go back to logistic regression just for a little bit. So recall what the decision boundary for logistic regression was. Just to recap. I'm not going to go into it in much detail because I've already covered this. But so we have, you've got a bunch of parameters and a bunch of different features, right? Okay, so this is your bias term, like before. Okay, and then you have these guys here. These are, you have n features, you have n input, not features, sorry, you have weights, right? So these are parameters, you have n parameters, and then these guys here are your features, right? You have n features. Okay, so this defines what the decision boundary, that separates between the two classes. Or if you had this in vector representation, this is theta transpose x is 0 with x of 0 being equal to 1. So that's, just review like before. Okay. All right. So this, this decision boundary is the same for SVN. So this, same. So this decision boundary stuff is the same for support vector machines. So we're going to use this to go and cover a little more detail on what this stuff is. Okay, so let's say we're given, we're given some training examples, and there's m of them. So given m training examples, so you've got a bunch of input features and expected labels. So, this is same stuff as we covered before. You've got m of these. Okay. Okay? All right. So we've got m of these, and then what we're going to do is we're going to change the labels a bit. So in logistic regression, we had the negative class being 0 and the positive class being 1. We're going to change it slightly where the negative class is negative 1 and the positive class is positive 1. So instead of 0 and 1, we're going to go minus 1 and 1. This will make the math behind this a little easier to deal with. Okay? So the labels are 1 for the positive class, okay, and negative 1 for the negative class. Just gonna make it a little, this notation will make things a little easier to deal with. Okay, so 1 and then minus 1. Okay, so what we want to do is we want to find the parameters, theta 0, theta 1, up to theta n, right, for the optimal hyperplane. So these define the hyperplane in n dimensions. Okay? Okay. All right, so I'm just going to crack open some linear algebra theory. You can just take my word for it that this is true. If you like, you can review it on your own. But in linear algebra, the vector, so if we can represent these parameters as a vector, right? So you have theta 0, theta 1. You've got an n plus 1 element vector. Okay, these is a normal or perpendicular vector to the hyperplane. Oh, hyperplane, sorry. So when you talk about linear algebra, there's a way to define a plane. So there's what's known as a normal vector and a point on that plane. So when you define this vector in terms of linear algebra, what you're doing is you're defining a vector that is normal or perpendicular to this plane. Okay? vectors of the hyperplane. Okay. Okay, so this is usually normalized. It's usually, the length of this is 1. This is usually normalized. Or the length is 1. Okay, so we usually, the notation is usually normalized, so the length is 1. Okay, so when we're talking about the separable case, so we've got that optimal hyperplane. Okay, there are 2 additional hyperplanes that we can define that are parallel to this optimal hyperplane. There's one additional hyperplane where it will be just along the boundary of where the positive examples would be, and then there's another hyperplane where it would just be along the boundary where the negative examples would be. All right, so we can define 2 more hyperplanes. So if the data is linearly separable, so we can define 2 more parallel hyperplanes to the optimal one. Yeah, there's two more that we can talk about. Okay, there's one where when you take, when you find the decision bound, it's offset by positive 1, and then there's one where it's offset by -1. So this is for the positive classes, and this is for the negative classes. I'll show a diagram in a minute. I just want to put this notation out there. Okay, so each of these hyperplanes, are designed to separate between the 2 classes, such that the boundary is just barely touching as few examples as possible. So each of these hyperplanes are designed to separate, let's see here, the 2 classes as tightly as possible. Oh, sorry. Okay, so they're supposed to separate them as tightly as possible. Okay, so let x, so we've got x0, x1, xn, be a let's let it be an example. Let's see here. That is the closest to a hyperplane, to one of these hyperplanes. Okay, so we're gonna just let some arbitrary example, but they're gonna be as close to the hyperplanes as possible. Okay, so the set of any of these examples that actually touch one of these hyperplanes are what are known as support vectors. Okay, these are support vectors which define the 2 hyperplanes that separate between the 2 classes. So that's what a support vector is. So that's why it's called support vector machines. So the set of all training examples that are the closest to any of these hyperplanes. So we've got 2 hyperplanes that we've defined. I'll show you a diagram very soon, just to put things together. Is called the support vectors. So that's where the name comes from. Okay? Okay. So just some notation before we start. So for SVMs, the best parameters, I'm not going to prove this, it's actually part of the framework, it's the properties of the framework. The best parameters to get the right hyperplane, or the optimal hyperplane, is represented as, so theta transpose x, the length or the absolute is equal to 1. Okay? So this is what is known as the canonical hyperplane. Okay. Okay, so here's a property that I'll talk about, and then I'll show you a diagram. Okay, so I'm not going to derive this, but there is a formula, or there is a derivation you can figure out that figures out the smallest distance, or the best distance from a point to a plane. So I'll talk about that in a minute. So from linear algebra, the distance from a point, which I'll call x, that we talked about before, so from a point, so x to a plane, which we define as theta, is the following. So the distance is, you take the dot product of the, between the parameters and the vector, and then you divide by the length. And this is actually equal to theta transpose x, right? Because the dot product is just equal to a vector transpose times itself, well, not times itself, but times another vector. And we define this to be 1. This is equal to 1 from before. Okay? So the distance is 1 over the length here. Okay? And so this, this point here, this is actually, this point is a support vector. Okay? So this defines the minimum distance from a point from one class to the hyperplane. So the margin is defined as twice this much. Okay? So therefore, the margin is simply twice this distance, or it's just 2 over that. Okay. This is, it's not bad. Okay, so I've got a nice diagram to show you that I'll, consolidate all these things together. Okay, so let me just put it on the next slide, because it's actually quite large. So here we go. I pulled this off from Wikipedia, which is very nice. Okay, here we go. Okay, so there's a lot of stuff going on here, which I'll describe in a little bit. So this here, this is the optimal hyperplane. Okay, and the notation's a little different here. They wx minus b. So what this is, that w is your vector of parameters without the bias, and then x would be a point support vector, and then b would be the bias itself. So this you can think of this here as theta transpose x equals 1. Here this is theta transpose x is minus 1, and this is theta transpose x equals 0. Okay, so this is the optimal hyperplane. This is the one for the positive classes. Okay, this is for the negative classes. Okay, and this is what's known as the margin, right? So absolute omega w is the same thing as the length of the vector here, and this is what's known as the margin. Okay, this is the normal vector to the plane, to the hyperplane. Okay, and then you have these two, and then these things over here, these entities here, these are the support vectors. Okay, so these are the examples, or these are the training examples, or the points where those are the points that require the least amount of separation between the two classes. So wherever these two hyperplanes touch those examples, those are what are known as support vectors. Okay, so you have the support vectors here, so that means that this region here, this region is for the positive class. Okay, and then this region here is for the negative class. And this is just for two features for now. Okay, so we've got that, we've got the margin, and then this is the optimal hyperplane here. Okay, so that's nice. So let me just write down some little bit more notation here. So, so that's a diagram for two features. So for the positive class, let's see. Good. I've got a couple more slides on them. So for the positive class, so what we need to make sure is that for our training example I, we need to make sure that when you when you find the weighted sum, when you find the decision boundary, it's got to be greater than 1. It's going to be on the one side of the margin. Okay, so if and then so you've got those two hyperplanes there, and then for the negative class, you got to make sure that when you find the decision boundary, it's less than -1, right? If you know, it's superfluous there, but it's fine. So for the negative class, for the positive class, that's cool. Okay? So you've got that. Great. So this states that each example must be on the right side. So this is what's known as, it's going to be on the right side of the margin, so to speak. So it's got to be, you got to be sure that it's on the right region, or the right, you know, the right side of the hyperplane in order for it to be successfully matched or successfully classified. Okay, cool. Okay, so what we can do is we can rewrite the above as, so instead of just having, you know, these different cases, you can consolidate it into one case. So you can actually just represent it like this. Okay, so you can do that instead. It makes sense because if you have the positive class, so if y of I is equal to 1, then you want to make sure that the product between these, or the dot product, is greater than 1. That's cool. Okay. If the class is negative, you're going to have a minus 1 here, then we need to make sure that this product is negative, so when you multiply two negatives together, you still get a positive number. So we can combine these conditions here into a single statement, like that. Okay, so if it's positive, then you got to make sure that the dot product is positive. If it's negative, then you got to make sure that the dot product is negative as well. So when you multiply those two numbers together, you still get a positive statement. So when you combine those two, you get that, which is cool. All right, so so we know that the margin, right, is defined as, you know, it's twice the length of the actual, you know, length of the vector itself. Sorry, let me just turn this to black. Okay, so if you want to make this distance, if you want to make this margin as large as possible, then what you want to do is you want to make this length, this vector here, as small as possible. Because when you take 1 divided by, or some number divided by a very small number, you're going to get a very large number as a result. So if you want to maximize the distance, if you want to maximize this margin, you want to figure out what the smallest length of this vector would be in order to maximize the margin. Okay? So we need to minimize. Okay, we need to minimize the length of the parameter vector, which is this guy, okay? As small as possible. Okay, so that is our objective here. We need to make this length as small as possible if you want to increase the margin to be as large as possible to separate between the two classes. It's a large margin classifier. Okay, so therefore the cost function is this. So we need to, so we want to minimize the length, but we're going to do it squared because it'll allow us to, you know, when you're finding the gradients and all that, it makes things easier. Okay, so we want to minimize this such that So you want to minimize this length, but you want to make sure that when you find this vector, when you find this vector of parameters, you want to make sure that when you classify each of the training examples, they're on the right side of their hyperplanes, right? So not only do you have to minimize the length, you got to make sure that when you classify all your training examples, they're on the right side of each hyperplane, okay? So such that, you know, for all training examples, okay? So this is the cost function you have to minimize. And minimizing this is beyond the scope of this course because this is called constrained optimization, and the techniques that you'll learn so far in your classes here, they don't actually cover this. It's actually quite advanced, so we're not going to solve this in this class. Okay, so I'm just going to get you to actually use the SVM package to do that yourself. Okay, so this is what is known as a hard margin or linear classifier, because we are assuming that these examples are linearly separable. Okay, so this is what's known as a hard margin or a linear classifier. So solving this cost function is beyond the scope of this course, so you don't have to do this. And there are so many different efficient SVM packages that implement this successfully, and they're quite fast, that it's kind of like, reinventing the wheel again, so just don't do it, okay? So use already available tools to solve this, okay? All right. So I'm going to talk about one more thing. I actually just have a couple more things, and then I'm going to take a break here. Okay, so this is the situation where the data was linearly separable. So there is a clear decision boundary that separates between the two classes. But I haven't talked about the nonlinear case. What happens if the decision boundary is nonlinearly separable? Like you saw in the first part of the lot number 2, where you have that kind of weird kind of circlish decision boundary. Okay, so here's another question. What if the data is not linearly separable? What do we do here? This is the question that we haven't asked ourselves yet. All right. So what we're going to do is we're going to use a well-known, use a trick called the kernel trick. Kernel trick, yes. All right. It's derived from what are known as kernel methods, which is a very popular statistical algorithm, which is, again, beyond the scope of this course. And I just want to break it down to you very slowly, or just the bare bones. So what the kernel trick does is that it takes your data, which is originally non-linearly separable, it transforms it in such a way where the data actually becomes linearly separable. So it does a little transformation where it makes the decision boundary linear in that space, so that you can find the right weights for the SVM, so that you can find a large margin hyperplane. Okay? So what we do is we use kernels to transform the data. Right, so we use that to transform the data so that the data becomes linearly separable in this new domain. Okay? So once you transform this data, you find the optimal hyperplane, or you find the optimal parameters in this new space. And then if you wanted to classify new inputs, what you'd have to do is you'd have to take your you have to take your normal features and transform them using the same kernel to this new plane of existence, and then you figure out, using those weights, which side of the hyperplane you're on to figure out what class it is. Okay? So once you transform your data, okay, you minimize the cost function with this new data. With this new data. So you get the weights in this new space, and then you just, you use that to make predictions. Okay? So the cost function will change to reflect this new transformation. To reflect this new transformation. Okay. As people say, a picture's worth 1,000 words, so let me just show you what a picture of this looks like. Okay? So, let's see here. Cost will change to reflect the new transformation. Okay, so it's going to look like this. Pull this from Wikipedia as well. Okay. Oops. I like to resize this. Okay, here we go. So I pulled this from Wikipedia, all right? So this is your data that was originally non-linearly separable, and then when you apply, so phi here, the convention phi, this is what we know as, this is what's known as a kernel function. When you take all your points and transform them using this kernel function to a new space, the data actually becomes linearly separable. It's actually, the proof of this is, I'm not going to just take my word for it that it works. The proof is actually very complex, which I won't bore you with the details. Okay? But this kernel function, what it does is, the goal is that it takes data that is initially non-linearly separable and transforms it into a new space where the data does actually become linearly separable, and you can apply SVMs to this new data. Okay? So this is the, sorry?
Is there any reason why we don't use this kernel function for multivariate regression or something what we did before?
The reason why is because when you decide to transform it into this space, what will happen is that you have to design the right cost function to minimize in order to take advantage of this. So we actually didn't, so the cost function will actually have to change. What we did before with the linear stuff is that we minimized the cost function, but we didn't have any of these constraints, making sure that each one of these points belongs to one side of the hyperplane or the other. So you have to modify the cost function. Then when you do that, you might as well just use SVMs instead. Okay? So yeah, so the point of transforming this is because you're using this to minimize a new cost function that takes advantage of this and also make sure that each of the points are on each side of the hyperplane. But so just transforming it is one side of the story. The other side is to figure out what the right cost function is. So the cost function we had before, it doesn't take advantage of this stuff, and you have to modify that. And then if you do that, you might as well just solve the SVM problem. Yes.
What's the advantage of transforming it to linear? Like, what's wrong?
If you don't transform it, then the SVM cost function is actually not solvable. So that's why you have to transform it. So it's not solvable. It's just it's a lot harder to solve, and it takes a longer time. So if you transform it first, it's actually easier to solve. Okay? Those are very good questions. Thank you. So you have this kernel function. All right. So how do we do this? So I'll take a break after this point. So how do we do this? So what we need to use a kernel function. So this will be my last point before I take a break. Okay? So we're going to use a kernel function which is called phi that are between two training examples, x of I and j. Defined between two training examples. Okay? So two training examples. And then what we do is we transform the data from n+1 features. Right, so this includes the bias. So we're going to transform this from an n-featured, n-dimensional feature vector to a m+1 dimensional feature vector. So m is the number of training examples. m+1, from m+1 to m+1 features, sorry. Okay, sorry, can't write here. Features. Okay, and this is the number of examples. Okay, and this includes the bias. Okay? Okay, so you transform that from n+1 to m, and then what the kernel function does is that it measures the similarity between two inputs, or two examples. The kernel function measures the similarity. This will be my last point, and then I'll take a break, all right? Similarity between two examples, I and j. Okay, okay? So what you're going to do is you're going to transform this into a, well, I'll talk about that after, but the kernel function, it just measures the similarity between these two examples, and I'll show you how we use this kernel function to transform stuff after the break. But I'll continue on after.